Welcome to the next lecture of this subject, Signal and Systems. We start with Unit 2, and here we focus on what are called linear time invariant systems. Such systems are of practical importance because we can learn about various system properties easily. The modeling of almost all practical systems can be done using the concept of linear time invariance. We have previously also introduced the concept of linearity and time invariance from the system of equations that represent the functioning of a system. So if yt is the output of the system and xt is the input of the system, based on the relationship between yt and xt, we have already formed the basis of linearity and time invariance. So now we are to study a special class of systems which follow both the properties linearity and time invariance. Linearity, that is to say the system is linear, means that it follows the property of scaling and it also follows the property of superposition. So if these two properties are being followed by the system, we say that the system is linear, which is to say if I have a system where I apply xt and I get yt, so if I apply any constant multiplied by xt, I will get the output also multiplied by the same constant. Similarly, if I apply two inputs, so I get for x1t, suppose I get y1t, and for x2t I get y2t. So if I apply x1 of t plus x2 of t, the system shall give me y1 of t plus y2 of t. So when these two properties are fulfilled simultaneously, then I say that the system is linear. Similarly, as far as time invariance is concerned, which is a very important aspect again, so if I apply the input xt, I measure what is the output yt. We have actually framed that if I apply xt minus t naught, that is the shifted version of the same signal at the input, the output which was generated originally will also be shifted by the same amount, then the system is said to be time invariant. And if a system follows both the property of linearity and time invariance, I say that the system is linear time invariant system. And in coming part of the series of the subject, it will become even more clear why such systems are important. In order to characterize linear time invariant systems, LTI systems, it is important to introduce some basic definitions which will be used to model such systems. So first of all, we take up the case of discrete time systems and we introduce something which is called h of n. H of n is called the impulse response of the system, which is basically the response of the system when at the input I apply unit impulse signal. So if this S represents the system, and understand and always maintain that we are subjected to linear time invariant systems only. System cannot be nonlinear, the system cannot be time varying, the system is supposed to be linear and time invariant. Then if at the input we apply xn, since it's a discrete time input, which is equal to delta of n, and I measure the output, then this output is written as h of n, which is called the impulse response of the system. This will be a basic definition using which later on we can in fact model the complete system. So h of n builds the basis of LTI systems. Another concept which is less traversed but is also supposed to be introduced is of step response. So again, for discrete time systems, the step response is given by S of n. N is the time indexed and S is the signal. So what is a step response? Similar to impulse response, the response of the system when we apply unit step signal at the input. So here also we have system which is discrete time LTI system S. I apply xn, which is u of n, and I measure what is the output. So whatever is the output, we represent that with S of n. So the basic definition yields, if at the input I apply unit step signal, I measure the output is represented by S of n, and S of n is basically the step response of the system, which is used for characterizing the LTI system properties. This is as for discrete time systems. The same definitions exist for continuous time counterparts. So suppose we have an LTI system which is continuous time system, which means that the signals that are presented as input and output are continuous time signals. Then we can similarly represent and define what is called the impulse response of the system. The basic definition remains the same. The impulse response is the response of the system when we apply unit impulse signal at the input. So if this is my system, again I apply xt, which is delta t, and I measure what is gyt, which is the output, and I write yt to be ht, and this ht is called the impulse response of the system, and it is the basic definition used for characterizing linear time invariant systems. Similarly, we will have step response of a continuous time system, which is response of the system when unit impulse signal is applied at its input. So So if I have a continuous time system S, at the input I shall apply xt is equal to ut. I measure the output yt, which is denoted by st, and st is the step response of the continuous time linear time invariant systems. What is the relationship between the two? In continuous time and in discrete time, both we will see. So if I have to define it for continuous time systems, ht is the impulse response, st is the step response of the system. The relationship is built on the relationship between unit impulse and unit step signals. So we know that unit impulse signal is the first order derivative of unit step signal, and the unit step signal is integral of unit impulse signal. This brings the relationship between impulse response and step response of the system. So ht will be equal to first order derivative of the step response. So unit impulse response of an LTI system is equal to first order derivative with respect to time of the step response of the system. In other words, if I have the unit impulse response of the system, I can calculate the step response, which shall be equal to st is equal to minus infinity to t h p dt. Basically the integral starting at minus infinity going up to t, because the step response is up to t, so the integral goes up to t of the impulse response. So if the impulse response, the independent variable of the impulse response can be denoted by some other variable, just to objectify that the time is t, and we integrate the function of impulse response. So integration of impulse response is step response, differentiation of step response is impulse response. Very straightforward. We can very similarly define it for discrete time counterparts. So if I have the step response and I want to calculate the impulse response of the system, in continuous time we have differentiation. So in discrete time there is no meaning of differentiation. It will, however, be converted to what is known as a difference. So if I want for discrete time systems the same definitions, it's very straightforward. The h of n, the impulse response of the discrete time LTI system, will be Sn minus S of n minus 1, which is to say we calculate the first order difference of the step response of the system. So whatever was derivative will become difference in case of discrete time domain. Similarly, this we are aware of, the integration shall become summation. So I can, if I want to calculate the step response using the impulse response, it will become summation k starts at minus infinity, goes up to n. Remember, this is the function of n, and therefore it has to be a function of n. And what we are adding? We are adding impulse response. So the variable of impulse response we have changed the summation variable to be k. So I just add all the values of hk up to nth instant to evaluate the step response of the system. So this is how these two are basically related to each other. In continuous time, we shall see just one quick word about it. So if I have ht is equal to e raised to the power minus at ut, which is the impulse response of the system, can I evaluate what is the step response of the system? We can do that using the same concepts. So what was the concept? That st is basically equal to integral minus infinity to t h of p dp. So I can just quickly evaluate this. It will be minus infinity to t e raised to the power minus a p u p dp, because we are writing now hp, right? So in place of t, I've just replaced t with p, standard protocol. What about this up? Up is the unit step signal. The independent variable is p. So as far as up is concerned, I can write that in brackets. So as far as up is concerned, up is either 1 for positive values of p, becomes 0 otherwise. So this is an integration with respect to p. So values of p that are allowed is only the positive values of p, at which up becomes 1. So I can replace up by 1 for p starting at 0 and going up to infinity, but the integration is not going up to infinity, it is going up to t only. So I can write st as to be equal to the integration now starts at 0 because the p variable starts at 0. It goes up to t, and I write e raised to the power minus ap dp. The integration of e raised to the power minus ap with respect to p becomes e raised to the power minus ap by minus a, and then we shall apply the limits 0 and t. So this becomes basically 1 upon a minus e raised to the power minus a t by a, and therefore the st which we are getting is 1 upon a times of 1 minus e raised to the power minus at. What are the values of t that are allowed is also to be focused, because if we have performed the integration from 0 to infinity, we should always appreciate that t cannot be negative. So st that we have derived exists due to ht, but the values of t that are there are to be positive based on the integration, because that we have used in the integration itself, and therefore we will multiply u of t with st, which then gives me this indication that it is only for positive values of t that st exists. Therefore, with the help of ht, I can definitely calculate the step response of the system, which, as we have introduced, is a basic fundamental to understanding linear time invariant systems. We can also cross-check our definition of impulse response with respect to step response. So if it is given that ht is e raised to the power minus at ut, which means that the impulse response is given. So we were able to evaluate the step response. The step response for this system is 1 upon a multiplied by 1 minus e raised to the power minus at ut. Now from the relationship between the two, it also happens to be that if I want to calculate ht back from st, the operation that need to do is first order derivative of st. So we can also verify this from this very example that if I calculate the first order derivative of what 1 by a minus 1 by a e raised to the power minus at, ut is just showing me that it exists at at a particular value of time, which is positive values of time. So there is no significance of ut here, and I can simply differentiate this part. So first part, if I differentiate, it's a linear differentiation, is a linear operation. So the superposition applies, which means it can be applied to both the entities separately. So if it is applied to the first entity, 1 by a derivative with respect to time is 0 because 1 by a is a constant. Similarly, the second part, it is minus 1 upon a e raised to the power minus at. That also will be differentiated with respect to time, and that differentiation shall yield me ht is equal to, so first part is 0, second part, the constant part, I shall remain here. It's the first order derivative of e raised to the power minus at with respect to t, ut shall remain. So therefore it gives me what, 0 minus 1 by a, and what is the derivative of this part? So it is minus a e raised to the power minus at and then multiplied by ut. So this gives me ht equal to, first part is 0. In the second part you can see a is cancelled by a, and I can directly write e raised to the power minus at times u of t, which, if we correctly remember, was the original problem. The original problem was that ht is e raised to the power minus at ut, and we want to calculate what is the st. So we have calculated the st using the relationship between ht and st, that st is integration of the impulse response. So integration that starts from minus infinity goes up to t of ht, using which we went on to calculate the step response, which is 1 by a common with 1 minus e raised to the power minus at common with ut. So ut has been applied to quantify that the step response is not for all the values of time, because in between the integral we have applied the constraint that t can only be positive, which means to say that if we apply something by ut, since ut exists only for positive values of t greater than equal to 0, and it gives me a value of 1, so it does not change the amplitude of this the remaining part of the signal, and applies that the restriction on time is there. So it is a great practice always to represent what is the time duration for which the signal exists, to multiply the signal with ut, which we have done. Also from introspection, it is clear if st has ut, st should have a ut. There is this part also there. So if ut basically makes it a causal signal. So if the signal is causal, if I take out any signal out of the causal signal, that signal also has to be a causal signal, which means that it will be right-sided, and therefore we apply VUT. But other than that, in integration, it was clear that the integration is from 0 to t, and therefore the only positive values of E are allowed, and therefore we multiply it by UT. But we also applied the inverse definition that HT is basically the derivative of the step response of the system. So whatever we calculated as step response, we differentiate it with respect to time once to evaluate the HT, and HT comes out to be the same signal. And therefore, it is proved that our basic definition of impulse response and step response and their counterparts are analogous to each other. Now, based on the impulse response of the system, we shall always be capable enough to characterize the linear time invariant systems. That we shall see in the next lecture. This is all for this lecture.